So here's that question. It's on page, is it 82? Anyway, I'll put it up on the screen. This is what I asked you to sort of finish off before today. And I've had a go at it, and I've made a mistake, all right? And just for once, it's a deliberate mistake. And I just wondered if, I haven't written the answers, but I just wondered if looking at that, whether anyone could see the mistake that I've made. So go on, Jodie, what's the issue?
It's the part B, after 10 years she will earn £25,000 a year, so she can't continue to earn £500 a year.
Yeah, she hits a buffer, isn't she? Although we've got to be careful about the after 10 years thing, because 20,000 is her salary to start with. So what would the 10th term in that sequence be? Do you remember it's 9 jumps? So it would be, the 10th term will be 24,500. So that's how much she will be earning. It's funny, isn't it? It's not after 10 years, that's the first year, so that's the 10th year. But, I mean, Jodie's absolutely right in the way she did her answer. What that means is that in the 11th, the 12th, the 13th, the 14th, and the 15th year, she'll be earning the same amount. So this is what we'll work out here. This is correct, all right? This is correct. So that gives me that. But my answer to part B is A plus 5 lots of 25,000. Okay? So for in the 11th year, the 12th year, the 13th year, the 14th year, and the 15th year, it's fixed. And you've just got to be careful with these wordy questions, because they often expect you to sort of do, sort of mental gymnastics like that. So let's just, rather than me working out, let me just put the actual answer up. There we go. Hopefully we've got something like that. So 222.5 I would have got, because I was working in thousands. That's what you get if you do the sum in black. That is correct. That's correctly using that formula. But the blue bit is the incorrect bit, because actually all I needed to do was to add 5 lots of 25,000 for that second bit. And that one reason why it's not a simple one, for some reason that this book puts that in loads of times, and it's just, things in the real world, surprise, surprise, don't often match that sort of regular pattern. So I think it's worth doing 3 more of these wordy questions. So we're on page 85, and I picked out 3, 7, and 8. And do you remember what I proposed? I proposed that when approaching this, it's a good idea to start by writing down any parameters you can work out, much in the same as we do with SUVAT problems. So we're on the I'm not sure it's worth it. I get £9 and 3p. So, well, no, let's just double check, because as we well know, I'm more than capable of getting it wrong. So n is 42, so you've got 21, n over 2, 2 lots of A is 1, n minus 1 is 41, and D is 1.
Oh, by times the 2, not plus the 2.
Right, yeah, no, I think on this one occasion I might be correct. And then with B, the first step I would take is to double everything, and remember that only means you need to double this. If you've got 3 lots of something, 6 lots of something is twice as much, you don't need to double the something, and that's going to give me a quadratic. And remember, when you get a quadratic equation with these sequences and series, you're going to get one solution that's meaningless. So yeah, see if you can proceed with that. And then have a go at number 8. I find questions like, sorry, number 7. I find questions like number 7, your head begins to spin. So maybe draw a picture. Actually sort of write down the sequence to start with to show maybe that's going to help. So I hope at home you can see the board this far. So you get a quadratic, solve the quadratic, you get 2 answers, neither of which are nice numbers, but we can ignore the negative. We don't get a whole number because there will be no point at which he will have saved exactly £100. So 140.92 means that after 140 days he won't have saved £100, and after 141 days he will have saved £100. I'm going to make a start on question 7. And as always, going to start by writing out some parameters. So the sum is just an application of the formula, and A denote the first year, you denote, ignore that. So you should get 13,608. Now I just draw a picture. That's all I do. I just draw a picture. I clearly annotate that, using this you've got 520 at the end of the first year. So you're adding 11 and then you're adding 11 again. Absolutely fine. There's a part C though, isn't there? Find the total commission paid to him in the second year. So could anyone suggest how what my parameters are going to be? So it's only in the second year. So help me out, Lily. What's A then going to be? If I want to work out the total that he earns in the second year, what will A be, the first term in that sequence?
First term, 11.
It's not going to be 11, no, because he's still earning.
Are we not doing B?
We've done, so B I just did by drawing a picture.
Oh, we just add to 11.
Yeah, that's right, yeah. Well, you clearly state what he gets at the end of the first year and then you just add to 11.
Oh, okay.
Yeah, I would.
You did say that.
So A for the first, let's be clear, this it's ridiculous, but this person is being paid a fortune, aren't they? Because they're still being paid for all these previous policies. So A is 531 and D is 11 now. And N is 52. So you've got this massive sort of, gazillions of pounds that he's going to earn. Well, perhaps not gazillions of pounds. A fair amount. So he earns 531 in the first week, and then 542 in the second week. And what we're doing is we're adding those terms together. So, with question 8, you're paying £500 for the first 50, and then for the next 50 you're paying 640, and therefore the total cost is those two added together. And then it says each subsequent extra depth costs £140 more. So the next 50 metres, which would take us to a depth of 150 metres, is going to cost me 780, another 140. So I'm going to get you to finish this one independently, because I think some of these arithmetic ones are really tough to get your head around. So I encourage you to have a go at that one independently, and perhaps we'll have a look at a solution to that one on Monday. Okay? You will notice, I hope you'll notice, because I hope I managed to keep it up, but I'm trying to feed you as much independent study as I can, just because, we need the practice. We need the practice. So that question 8, I encourage you to have a go at finishing that one in your own time, and we'll have a look at it on Monday. And don't forget, with the homework, I'm happy to have it electronically or in person. You can hand me the book in person. Right, let's move on then. Let's move on. I'd like to talk now about the ugly twin that goes alongside arithmetic sequences and series, and they are geometric sequences and series. And you may remember from GCSE that a geometric series is one where you are multiplying by the same thing each time. And I suggest to you there are 3 sorts of geometric sequence that we come across. So for example, here is a sequence where we are multiplying by a number bigger than 1. Okay, a number bigger than 1. We use A to stand for the first term. So in this case, A is 2. But we don't have a constant difference this time, we have a constant multiplier. And actually the word we use is we have a ratio between these 2 numbers and these 2 numbers and these 2 numbers. But it's the thing you're multiplying by each time. So we call that R. So in this sequence, R is 3. And so that means I can write a formula for the nth term in my sequence, a formula for the nth term, just like I did for arithmetic sequences. With arithmetic sequences, the 9th term was the first term with 8 jumps. It's the same here. If I want to get to the nth term, I take my first term and I multiply by r n minus 1 times, which looks like that. So that's AR to the power of n minus 1. So if I want to get to the 4th term, I need to multiply by r 3 times. So it would be the first term times r cubed. N minus 1 because I'm starting at the first term, so to get to the 15th term would be 14 jumps, or the 20th term would be 19 jumps. What's the other word we have, or the other phrase we use to describe something which grows in this way? Exponential growth. This is exponential growth. We know, we've come across this before, we know what it looks like on a graph. We know that when you are growing exponentially, things get pretty big pretty quickly. Unless we are dealing with a geometric sequence like this, where r is between 0 and 1. So in this case, a is 16, r is a half. Same formula for the nth term, but we know that this sequence is going to get smaller and smaller and smaller. And that is a consequence when in a moment we come to talk about series, adding these up. This sequence, if I add it up, is just going to get bigger and bigger and bigger and bigger. But this sequence, when I start to add it up, well, I get to the point where it's not really worth bothering to carry on looking for next numbers because they're getting so small. We'll come to that in a lesson or so's time. And the third sort of geometric sequence we come across, fairly rare I have to say, but they're ones that look a bit like this. So here I have a sequence where a is 2, but r is a negative number, in this case it's minus 2. So it's, the numbers are getting bigger, but it's flip-flopping between positive and negative. And if r was a negative number between 0 and 1, it would still flip-flop between positive and negative, but the numbers would get smaller and smaller. So when we look at geometric sequences in series, we just need to make sure we're aware of the fact we've got three different sorts. And to be honest, the last one is very rare, but exponential growth and exponential decay, we know are very, very common.
So you know you can plot growth and decay, can you not plot the last one then? 'Cause that's going to be...
Well, you could do. It would just look a bit odd, wouldn't it? It would sort of, if with this one, it would look like this, where sort of that would be an exponential growth, and if it was r was like minus a half, it would look like that, wouldn't it? Yeah, yeah. Okay, so the fact that we can write a formula for the nth term of a geometric series allows us to do the same sort of things as we were doing with arithmetic series, with missing terms and the like. So we're going to turn to page 67. I'm just going to work through a couple of these examples. So with part A, I have a geometric sequence. So I'm first going to write down my parameters. A is 3, R is 2. I'm asked to find the 10th term. So that's going to be the first term times 2 to the power of 9. From the first term to the 10th term is 9 jumps. And the nth term, that just means write the formula. So if I want to find the 10th term, I just do first term times the multiplier power of 9. And when it says the nth term, it just means write the formula, plugging in A and R. We're not going to do the second one, but the second one you can see has got R is minus a half. So this is where it gets a little bit more interesting, and for this one I'm going to draw a picture. So the second term is 4, and the fourth term is 8. So if I look at the jump between 4 and 8, I know that 4 multiplied by r squared has to be 8, because that's 2 jumps, isn't it? 2 jumps. So r squared has to be 2. And here's where they add the bit about common ratio being positive. So common ratio, R, that's what they're calling it. The square root of 2 is plus or minus root 2. And of course, we could have a negative number here. So this could be a sequence where R was negative, oscillating between positive and negative. But they're telling us it's not. So it's just the square root of 2. Now I could at this point work backwards and work out the first term, and then to work out the 11th term just do that times 10 jumps. But actually I don't need to. I've got the 4th term. So Beth, how many jumps will it be from the 4th term to the 11th term?
7.
Good girl, fingers. Yeah, 7. So that's times r to the power of 7. So yeah, so the 11th term, U11, is going to be 8 times root 2 to the power of 7, and our calculator will deal with all the malarkey. Exact value just means leave it as a set. Forgive me for barrelling through these examples, but I think it's worth trying to crack into some practice this lesson if we can. Any questions about this? So, my picture showed very clearly that to go from the 4th term to the 8th term, I was second term to the 4th term, I was multiplying by r squared. So I just used a bit of algebra to work out what r had to be, and then I worked out what I was multiplying by to get to the nth term. Just 2 more, and then we'll do some practice. Now a picture. So they're reassuring us that r is positive by telling us that all the terms are positive, so it's not oscillating between positive and negative. But what on earth is r? What on earth is r? Well, let me give you a trick, which is probably obvious to you, but there we go. If you can't see what r is, take any term and divide by the previous term. That's how we work out r, you know. What's that number divided by that number? That gives me the value of r. And I could do that in 2 ways in this sequence, because I know 3 terms. I could say, right, x divided by 3, that's r. Or I could have done x plus 6 divided by x. That's also going to be r, isn't it? The thing they multiply by here, or the thing they multiply by here. But here's the clever bit. It's the same value, isn't it? This and this will have to be the same. If this is a geometric series, or sequence, that's the same. So straight away, we've got an equation which is going to allow us to work out x. Possible values of x, it's probably going to be a quadratic equation, isn't it? Go on, have a go at solving it. I hate fractions, so I'm going to multiply by 3 and multiply by x. See what you can see if you can get somewhere with this, and then work out the 10th term. So multiply by x, multiply by 3. Do that in one go. There's no reason why you can't. Should have factorised, but it doesn't matter. Calculator told me anyway. So x is 6. That doesn't mean r is 6. That means x is 6. So now I can see the sequence, can't I? So a is 3, r is 2, I'm clearly doubling here, and we're asked to find the 10th term, so u10, that's the first term, times 2 to the power of 9. So, this is the key, one of the key skills, this finding out r if you don't already know it. And in this question it used use that to generate an equation which we then were able to solve. One more example. So I just wanted to rattle through these. I think this is. See if you can write down the parameters for this sequence. And then write down, using the formula that we talked about, the nth term formula. Can you write down a calculation that will allow us to work out the answer to this question? We came across one of these with an inequality yesterday, and I said you can use inequalities, but you can also use equal signs and just accept that you won't get a whole number. So use either. I'm going to use an equal sign. So A is 3, R is 2. Formula for any term is A r to the n minus 1. So I say, okay, let's work out which value of n, which term in the sequence would be 1,000,000. It's unlikely to be an actual value, so I'm probably going to get a value of n that isn't a whole number, and I'll know that the n value down is less than 1,000,000 and the n value up is bigger than 1,000,000. But I've got here a missing value in the power. So Grace, what technique are we going to have to whip out of the utility belt today to solve an equation where the missing value is in the power? Yeah, logs. Love a bit of logs. Remember, when we want to use logs, we've got to get the thing with the power on its own. So I'm going to divide by 3 firstly, and because that's not a nice round value, I'm going to and we have a choice at this point. We can do generic log logs, log to the base 10 of both sides, if we choose. But because we're feeling a little bit sophisticated these days, we could say, okay, what base, log to the base what, is the opposite of 2 to the power of something? Tegan, what base will I use if I'm trying to undo 2 to the power of something? Log to the base what? It's an obvious answer.
It's just 2.
Log to the base 2, yes. So I can do log to the base 10 of both sides and use the third log rule to get the n down from the power. But if I take log to the base 2 of both sides, that's the opposite of 2 to the power of. So on this side, I just get n minus 1. And on this side, I get log to the base 2 of 1,000,000 over 3. 1, 2, 3, 4, 5, 6. So n is just the log of that plus 1. Just check you can do that on your calculator. We need to be able to do logs with different bases. And we've got... do I do log with any base? So, oh, thank you, yes. So Yeah, so if you're in your run matrix mode and you press your math button, which is F5, you then have a thing that says log AB. Do you see that? Excellent, yeah. So you should get 19.34. That means that 19, the 19th term will be less than 1 million, so the 20th term will be the first one that exceeds 1 million. Can I just say, so you've got that one question to have a look at. If you want even more practice, Maths Genie, we're into A-level revision now, not AS, so good old Maths Genie. We scroll all the way through the AS stuff because we're through there. They've got a really good section on arithmetic sequences. So that's just a page of question on arithmetic sequences alone. So that's really good practice, end of week practice if you wanted on arithmetic. Don't worry about the other stuff yet. We've got some other stuff to do, but you could certainly have a go at that if you wanted. Focus on the homework firstly though, because I'd really like that for Monday, please. Thank you.
Yes, it would do a day at school.